Hello, my name is Viorel Ungureanu from Polytechnica University of Timișoara, and I'm going to present you the paper Numerical Investigation on Built-up Cold-form steel beams for long spans, paper prepared together with my colleagues Ioan Lukacevic from University of Zagreb and Ioan Dubina from the Polytechnica University of Timișoara. The objective of the paper is to present new research developments on the built-up cold-form steel beams of corrugated web using as connections spot welding, but now we are looking at the extension for long-span beams. Several years ago, we had the idea to create such a built-up element with corrugated web, but 100% composed by cold-form steel elements, avoiding the combination of two types of products, hot roll and cold form, having a high protection to corrosion due to the fact all the components are galvanized, and finally to develop a structural system suitable for automated prefabrication, reduced time, mass production, and possibility of high precision and quality control. We have started several years ago to investigate experimentally a number of 12 beams, 5 with screws, connected with screws, 2 connected with spot welding, 3 connected with CMT, called metal transfer, and 2 having openings on the web for various other purposes. The paper today will concentrate on the solution using spot welding. So you can see here the components of the beam. You can see the lip channels, the corrugated web, the panels for the corrugated web, and at the ends there are placed shear panels due to the fact the beam is fixed at the ends. The dimensions of the flanges were 2 back-to-back lip channels of 120 with a thickness of 2. The shear panels are flat plates of thickness 1 or 1.2 millimeter. We introduced reinforced profile under the load application, and the bolts to connect the end plates of the beam were of diameter 12, grade 8.8. And you can see here the difference between the two beams connected with spot welding, the position of spot weldings in order to prepare the seam fastening of the corrugated sheets used for webs, and the position of the shear panels. Together with this work, we have done tests on base material and also an tensile shear test on lab joints welded specimen, 100 specimen, in order to cover all type of combination of thicknesses that can be found in this built-up member. And as an exemplification, I can show you here the results obtained for a first specimen. And you can see here the initial slope, the maximum force, and the force displacement curve. Based on that, we started to validate our numerical model and then to assess some parameters to see the effect of imperfection, the effect number, position and distance of the spot welding, effect of thickness of the flanges, of the corrugated web, and the shear panel. Before investigating this, let me give you some information about the numerical model. We run geometric and material nonlinear analysis, including the effect of initial imperfections, so GIMIA analysis. The material was converted to two-stress through strain curve, and you can see here the transition. And we use 3D shell elements, SR, S4R, and the global mesh size was ranging between 5 to 15 millimeters. Also, we look for general contact. Normal direction was considered as hard, and transversal direction, the friction coefficient 0.1, and separation after the contact. We try to model the boundary conditions as we had on the experimental test. And for spot welds, we define them depending on the tensile shear test on the simply specimen as attachment points. You can see here the connection between the attachment points when defined using point-based fastener. Bushing connector elements were used to model the spot weld. And you can see here the first comparison, including the effect of initial imperfection, L over 500, 1000, 1500, and you can see here the agreement between the experimental and numerical curve are quite well, and also the deformation represent the same mode of failure as found in the experimental work. Looking to the parametric study, we were looking to the influence of number of spot weldings, 2, 3 every corrugation, and the results show a small influence of the 3 spot welding in comparison with the 2 spot welding. Then we were looking to the distance between the spot welding. We extended as much as possible the distance between the spot weldings, and the results show minor influence of the distance. This situation is just a theoretical one, could not be found in practice. Then we were looking to the influence of corrugated web thickness. We used 3 different thicknesses for the corrugated web, and what we observed that for very thin webs, 0.8 millimeter, the buckling occurs at very early stages. Then we looked to the influence of flanges thicknesses, and we changed from 1.2 to 1.5 to 2 and 2.5, and you can see here the force displacement curves for this. And significant influence can be found if the thickness is less than 2 millimeters. And at the end, we were looking to the influence of the shear panel thickness. We changed the thickness from 0.8 to 1.2 and 1.5, and we observed that the shear panel can influence the ultimate capacity by 15%. Now we can go to look for the long span built-up conform steel corrugated web beams, and in the paper we were analyzing 2 different spans, 12 meters and 27 meters. Due to the symmetry, only half of the span was modeled, and we were looking to several parameters like beam inclination from 0 to 6 degrees, shear panel thicknesses at the end of the member, the height and thickness of the lip channels used for flanges, the thickness of the corrugated web, and finally the number and distance between spot welds on the flanges. Lateral torsional buckling has been prevented in this analysis. In case of beams with 12-meter span, we were considering 2 different heights of the beam, 600 millimeters and 800 millimeters, while for the 27-meter span of 1,350 millimeters. In terms of flanges, for 12-meter span beam, we used lip channels of 120 and 150, while for 27-meter span, lip channels of 350, the height of the cross section. All the flanges of the lip channels were having the thickness of 2.5 millimeters, and the shear panels were either 0.8 millimeter, either 1.2 millimeter. The steel grade for all the elements of 0.8 millimeter was S250, while for the others 350, as we use in the experimental work. If we look to the results we obtained, we can see here the influence of shear plate and corrugated web thickness. We use shear plates of 0.8 and 1.2 and corrugated web of 0.8 and 1.2. You can see here the results for a degree of 6, and what we observe here that the increase of height leads to an increase of the bearing capacity and rigidity. So here we have a height of 600 millimeters, here 800 millimeters, but the beam is not sensitive to the shear panel thickness as in case of horizontal position. If we look to the beam inclination, we can see here 2 groups of curves. For 600 millimeters, the height of the beam, we're using 0.8 corrugated web in one case and 1.2 in the other case. What is clear that the beam inclination influences the value of the value and the rigidity, the ultimate force and the rigidity of these elements. So a major increase of rigidity and of the maximum force was observed for the 6 degrees inclined beam. And looking to the influence of numbers of spot weld on flanges, we use 2 spots or 4 spots welding, and you can see here the results for on the left hand side 0 degree inclination and 6 degree inclination for end 800 millimeters the height of the beam, while in this case you can see the same but for the slope 0 and the shear panels of 1.2 millimeter. What we observe is that the number of spot welds on the flanges has a minor influence on the response of the beam. The flange thickness increase leads to the increase of the capacity of the beam, but for thicker flanges, the inclination of the beam influences the behavior of the beam by eliminating the plateau after the yield of the beam. Finally, as conclusions, the results of the experimental and numerical program on built-up cold-formed steel beams show that the resistance of such elements is governed by a number of parameters due to the multiple parts involved in the number of possible beam configuration. And particularly to these results, the obtained results highlight the aspect of the behavior of long-span built-up beams. Besides the failure modes observed in the experiments, the distortional instability of the flange profile occur. The failure of the long-span beams is caused by the concentration of the internal forces in the supporting points, while the stress level in the corrugated web is smaller. The number of spot welds does not have a major influence on the global response of the built-up beam. The inclination of the beams for a pitch roof has a beneficial effect on the capacity of beam due to the redistribution of internal forces. The current conclusions are valid for the case study in this paper, but several other investigations are needed to investigate some new parameters and an optimized solution.